So in each pair, we have enough time to finish the concept check today. Which has the most negative electron affinity? Is it going to be lithium or beryllium? Is it going to be fluorine or neon? Is it going to be carbon or nitrogen? So each one's like its own problem. This is like a problem. This is like a problem. This is like a problem. So based on what I just discussed, see if you can figure it out. Which one would be what? Based off of the trends, and don't forget the exceptions. Anyone have any idea between lithium and beryllium? Which one is the most negative electron affinity between those two? Yes, lithium is higher, definitely higher, has a more negative electron affinity, which would be a higher electron affinity because we think about them as exothermic values. Remember, the beryllium was one of those exceptions. You would have to add it into the 2p, so that causes more repulsions. Okay, so that one is definitely there. How about fluorine and neon? What do you think of those two? Yes, fluorine, good. Why not neon? Anybody want to explain why not neon? It's a noble gas, good. So it already has its established 8 valence electrons, or in the case of helium-2, and it is a positive electron affinity. It doesn't want to gain electrons that would cause instability. These guys always have positive electron affinities. You saw that on the chart, so they're not going to have negative values. Carbon or nitrogen? Good, carbon. Nitrogen also is one of those exceptions we just talked about, where you have to double up the one in the 2p here. You have to put, here's nitrogen originally, but then you have to add this other one here to that orbital, causing those repulsions. Exactly right. And those would be the correct answers. Okay, atomic radius. Looking here, what is the size of the atom actually? Well, it's really a measure of 1/2 the distance between them being covalently bonded together. So 1/2 of this distance, which is a tad bit shorter than the actual radius because the overlap in the cloud here, but basically just know it's about the radius size almost exactly in terms of the atom here, but it's really measured off of this distance between nuclei of the covalently bonded pair. Now, some things that you need to know, that the reference atoms in terms of picometer, which is 10 to the minus 12, they could do it in angstroms, which is 10 to the minus 10. They could use nanometers, which is 10 to the minus 9 in terms of those metric units, very small when it's talking about like things like this that are really tiny. Angstroms has the capital A with the little circle on it, you know, nanometer. We're also going to use that measurement where we're talking about waves and wavelength and energy calculations for the electrons in unit 3. And then picometer, 10 to the minus 12, really, really small. In general, as we go across a period from left to right, the atomic radius decreases. The effective nuclear charge increases, or that Zeph number. That's because you're adding more protons. So it's the same rule as before. When you add more protons, your effective nuclear charge increases, and you're also increasing the attractive force, drawing in closer those electrons. That increased attractive force will pull it in closer. So if you're using the coordinate plane from last year, atomic radius goes here. So it increases if you go left, increases as you go down. It's opposite where ionization energy, electron affinity are over here, electronegativity are over here. Those trends would be over here in the upper corner where they increase as you go up and increase as you go to the right, if you're using this tool to help you remember the periodic trends. In general, as you go down a group, it increases as you're going down. And as we go down a group, it's the same reason as if it were ionization energy or electron affinity. We're really talking about the orbital sizes, increase in number of principal energy levels, principal quantum numbers, n, that n equals, okay, principal energy levels. Now, remember, we could also phrase this in terms of Coulomb's law, Q1, Q2 over R squared. If we're talking about adding the protons, you're adding charges to the top. If we're talking about adding principal energy levels, you're increasing the distance, okay, which also would lessen the pull of the nucleus. You can refer to Coulomb's law here. And by adding more principal energy levels, you're also adding in shielding, which is lessening the pull of the nucleus on those outer electrons and makes the atom larger, makes it a wider radius, larger atom. Make sense? So the reasons really don't change. We're just describing a different property, in this terms, the size of the atom, the radius. And here's a nice graphic here showing you atomic radius for selected atoms, as you can see as you go down the group. This is like the snowman idea. And then the toppled over snowman, it decreases as you go to the right here. Helium, the smallest one on the table. And then I think, you know, if we added francium down here, it should be the largest one on the table based off of the properties. But as you can see, the different values here, I don't know if this is picometers or if this is angstroms or exactly what that number. I think it's picometers, but as you can see, the size here definitely follows that particular trend. Let's practice. Which should be the larger atom? And then don't forget the why part, the good explanation part. Is it going to be sodium or is it going to be chlorine? What should I pull up and look at first before I make my decision? The periodic table. Good. I should look at that periodic table. Let's look at the periodic table. So yeah, let's do that. Where is our sodium? Oh, it's right over here. Where is our chlorine? Oh, it's right over here. So what do you guys think? Sodium, good. Now why sodium? Now we have to explain the why. Why sodium? Remember, this is side to side here. Yes, chlorine has more protons, good. And yes, we're looking at the attractive force of the nucleus, exactly right. Chlorine has 17 protons, sodium has 11 protons. We would say sodium has less protons, less attractive force. If you're referring to Coulomb's law, you would be referring to the Q1, Q2 part of the equation. Less magnitude of charge, so the force decreases. All of those would be good ways to explain this one. And this is a typical free response question. You will see a periodic trend question that you will have to explain on the quiz. So because the electrons are not attracted, the lower effective nuclear charge, less protons. All right, like I said, you could also use the Coulomb's law version of the explanation. Correct. Which would be the larger atom, lithium or cesium? Once again, looking here at our periodic table, we need to locate these elements. Where are they found? Where do we see them? Group 1, right. So lithium right here. Going down the group, we see cesium. And that's going to tell us which one is the larger atom. Correct, the cesium. Now we have to explain the why. So going down the group, up and down the group, what's the reasoning there? What do we need to look at? More energy levels, more principal energy levels, more shielding, yes. Farther distance, all of those things are good things to cite. So it's larger because an increase in orbital sizes due to successive principal energy levels to accommodate more electrons, more shielding. And you could also say the farther distance if we're talking about the Coulomb's law explanation. You can always cite that too, this part, the farther distance part. Very good. Cesium's the larger atom. This is an interesting one. Let's think about it. Which is larger, the 1s orbital for hydrogen or the 1s orbital for lithium? Yes, hydrogen would be larger. Why would hydrogen be larger? Any idea why hydrogen would be larger? It doesn't ask for an explanation, but we could easily explain it. Why would hydrogen be larger? Yes, it has less protons, less attractive force, and lithium has a higher effective nuclear charge. Okay, so that doesn't attract them in as close. The binding energy on lithium, if you were looking at one of those photoelectron spectroscopies, right? Say like the binding energy is higher over here or whatever for the 1s. You know, here's lithium. Hydrogen would be over here a little bit. Wouldn't be the same binding energy because lithium has 3 protons, whereas hydrogen only has the 1 proton. Now, let's look at and talk about the, so we would circle this one. This one's larger, which is lower in energy, not binding energy, just lower in potential energy is what it's referring to here. Yes, looking at the lithium 1s orbital, it's going to be lower in energy. We're kind of following the off-bow principle idea. Remember, you finished the lowest energy, fill the lowest energy level orbital first. And why is it lower energy, potential energy? It's because it's closer to the nucleus and it experiences more of that, that attractive force by the magnitude of charges. So it has more of attractive force as closer to the nucleus. It's at a lower potential energy. All right, so explanation here, bigger because the electrons are not as tightly bound, has a higher effective nuclear charge. You could also say hydrogen has less protons. Lithium orbitals lower in energy because the electrons are closer to the nucleus due to the higher effective nuclear charge, or ZEF. More protons. Very good. All right, quick exercise. Let's look at atomic radius and ionization energy. So, oxygen, fluorine, and sulfur. We definitely need to go look at our periodic table. Looking at the periodic table, and we need to find oxygen, fluorine, and sulfur. As you can see, they typically group these elements together in a question like that, so you have an easy reference point. So we see them all over here in this upper corner together. Now, what does that mean in terms of ionization energy? No, yes, ionization energy is the first one. What's the trend for ionization energy? We need to arrange them in order of increasing. So what's the trend? Ionization energy increases to the right, and it increases if you go up the group. Yeah, up the group and to the right. Remember, if we're looking at our coordinate plane here, ionization energy is 1 up here, so it increases if you go up, increases to the right. So in that case, we want to put them in increasing order. Which one has the smallest ionization energy? Sulfur. And you can also write it like this with like the little less than signs. Then comes oxygen, yes, you're correct, and then would be fluorine. You could write it in that, or you could just list them in order, like so. How about atomic size, atomic radius, which is, of course, this part of the plane. So left and down it increases. So which one is going to be the smallest? Yeah, Fluorine is the smallest in this case, then oxygen, then sulfur. So FOS, exactly right. Ion size, sizes of ions. Gotta look at those too. We're looking upon them in terms of also their proton number, their effective nuclear charge and attractive force. The number of electrons in there, that's important to consider, and the orbitals in which those electrons reside. What you're going to notice here looking at the chart here is you have, in this particular chart, you have the parent atom, the neutral atom, and then you have the ion shown. Here would be the parent atom for oxygen, and then oxide would be the ion shown. So this chart is showing you the comparison to the parent neutral atom. So cations, you can see over here, the dark orange ones are the cations, the neutral atoms are the yellower ones. They are smaller than their parent atoms. The outermost electron is removed. Repulsions between the electrons are reduced. So we're, decreasing. And it's also that outer energy level being removed makes the distance for the next electron to be shorter. And reducing those repulsions, of course, attracts it in further, attracts it closer to the nucleus. Anions get larger than their parent atoms. As you can see, oxide, fluoride, chloride, these guys are all much larger than their parent atoms. Why that is? Adding electrons causes repulsions. You're not adding anything, new energy levels or anything, you're just adding to the current energy level. And that's going to cause those repulsions, and the repulsions are going to make it spread out. And spread out a little bit more here, and you can see the numbers. Actually, it's quite a bit more, depending on how many electrons you're adding in terms of the size there. That's one way we look at ion sizes, comparing it to its parent atom. You can also use the regular trend if you're just comparing ions in a group. So if I'm comparing lithium ion with sodium ion, with potassium ion, with rubidium ion, if I'm comparing those, they generally increase as you go down the group, just like the regular atomic radius trend. And that's because the principal energy levels numbers grows, you have more shielding effect, you have farther distance, all the same reasons as you would apply for regular atomic radius. So as you go down a column, that's how it's going to look. Increasing value of the N, which is that principal energy level number. You could say shielding, you could say farther distance as well. So going down the group, as you see that too, oxide, sulfide, selenide, telluride, they increase as you go down the group. Same idea there. Across a period's a little bit different. When you're going across a period and you're comparing ions, you're looking at isoelectronic series here. Ions have the same number of electrons because remember, they're all mimicking their noble gas configuration. So looking at this particular one here, neon would be the noble gas. And it's not an ion, obviously, but it has the 1s2, 2s2, 2p6 configuration, which is what oxide's going to have, which is what fluoride's going to have, which is what sodium ion, magnesium ion, and the aluminum ion are all going to have. So if we're comparing them in the rows, we really reference it off of the nearest noble gas and look at it there. Ionic size decreases with an increasing effective nuclear charge. Remember, you're adding more protons. If you're adding more protons, it's the same reason as before with regular atomic radius, it's going to get smaller because there's a larger attractive force pulling in the electrons closer. So looking and comparing here, the aluminum, which has 13 protons, magnesium has 12, sodium has 11, fluorine has 9, neon has 10, and oxygen would have 8. So out of this entire series, oxygen should be the largest of them all. And it is the largest. And then aluminum is going to be the smallest because of that 13 protons. Now, your turn to go ahead and try to arrange them. Here, smallest to largest. This is between the third and fourth row, or third and fourth period. Let's take a look at the periodic table, and you can go ahead and start thinking about that. Now, which noble gas are we basing this set of series off of that we should look at and compare to? Argon, good. Yes, let's take a look over here at argon. So we have the chloride, sulfide, phosphide. We have scandium ion, calcium ion, potassium ion, all based off of this same electrons as argon, same configuration as argon. So looking there, out of those particular ones, scandium's 21, calcium's 20, potassium's 19, and so forth. So which one is going to be the largest out of our little series here that mimic argon? Largest would be phosphide. Yes, phosphide would be the largest because it has the least amount of protons. So I'd put that over here on this side. Phosphide's going to be the largest, right? Which one would be the smallest out of those? Yes, the scandium ion is going to be the lowest because it has 21 protons. 21 protons. All right, and then what's the next smallest that's next to the scandium? That would be, yes, our calcium. Then comes the potassium, good. And in the middle, of course, is argon, because it's the one everything's mimicking. Then comes chloride, yep. And last but not least would be sulfide in between. And I think this is like 15 protons. So the range of protons, as you can see, going there based off of that attractive force from the nucleus in terms of the number of protons and that effective nuclear charge. Properties of metals, nonmetals, and metalloids. Metals, nonmetals, and metalloids. Review of that real quick. It's not that important, but when we start talking about different solids and their properties, and some of these solids will be metals, we'll be addressing more of these in the next unit. Now I'm kind of drawing around here these metalloids because they're on the staircase. So they're kind of the breaking point between the metals and the non-metals. So as you can see here, these guys have properties of both. Hydrogen would be the only one that's not with the rest of the non-metals because it has one valence electron. So as you can see, they put a little space here though, because besides having one valence electron, it really doesn't have the same similar properties as necessarily these alkali metals. Metallic character increases if you go to the left and if you go down, which does kind of make sense here if you're looking at, say, the carbon group, group 14. You have non-metal, 2 metalloids, and then you have metals. So the metallic character is increasing as you go down the group. Metallic character also increases if you go left. So you're basically changing into more like a metal. And metals have certain properties and certain characteristics. Non-metals have certain properties and certain characteristics and so forth. So let's take a look at that. And the opposite is true as well. So if metallic character increases if you go left and down, that means non-metallic character increases if you go up and to the right. So those are opposite of each other. Different things to look at in terms of their properties, and remember, they have shiny, lustrous colors. They're almost silvery. Metals are malleable and ductile, so form shapes. You can pound it into shapes and sheets. Ductile into wires. They conduct heat and electricity. We'll talk about this more, like these properties apply to the metallic solids. Most metal oxides that are ionic solids are basic, meaning they will produce hydroxide in water. tend to form cations in aqueous solution, you know, like Fe2 plus or Zn2 plus or Mn, you know, +7, other different ones like that. Nonmetals, of course, do not have luster. They're usually various colors, like sulfur is yellow and phosphorus. There's like a white phosphorus and a red phosphorus, and there's a lot of nonmetals that are not solids because they exist as gas at room temperature. Like chlorine is a green-yellow gas and so forth. Solids are usually brittle. Some are hard, some are soft, poor conductors of heat and electricity. The nonmetal oxides that form acidic solutions, so they'll produce H's, H plus in water, tend to form anions or oxyanions. Oxyanions, we're talking about those polyatomic ones, like nitrate or sulfate, stuff like that. Oxyanions. Differences between, of course, revolve around these properties and their position, of course, on the periodic table. We'll look at this in more detail in the next set of notes too, because we'll be talking about the cation anion charges and they're distinguishing on their position on the periodic table where they're located. But the transition metals, this one highlights good ones about the transition metals. Some of them are multiple oxidation metals. Remember, they have more than one oxidation number, like copper and cobalt. You don't have to memorize these. What you would need to be able to do with them is be able to tell what their charge is in a compound. So, for instance, if I was, you know, I've had iron 3 chloride, which would be FeCl3 versus iron 2 chloride, I should be able to tell that that's going to be a +3 charge there because the chloride is -1, and I should be able to decipher that that's iron 3 as opposed to this one, which would be iron 2, because the chloride is still -1, but there's only 2 of them, so I should be able to tell what the charge is on that transition metal, that multiple oxidation metal. Don't forget that there's a few of them over here that are not in the transition section, like tin and lead. They mainly focus on these guys because, you know, they use them quite frequently. A couple of them are not multiple oxidation metals. Zinc only goes to +2, silver only goes to +1. They rarely ever use cadmium, but you know, you can remember from aluminum +3, +2, +1. Those guys always have those oxidation states. And like I said, you should just be able to tell it from the compound. So if you have, you know, ZnNO3, 2, you should be able to tell, well, nitrate's a -1, so the zinc is a +2 there from that particular deal. They're not going to make you name them, and they're not going to make you memorize stuff, but you should be able to tell from the formula what the charges would be. Don't forget names: alkali metals, group 1, alkaline earth metals, group 2, halogens are 17 or 7A, noble gases are 18 or 8A. Transition metals here in the D block, the lanthanides and actinides, they're called the intertransition metals or the F block. Basic things on the periodic table. I've referred to them multiple times, but definitely make sure you have those reference points as well. So I already talked about this, but you can go back through it. Good conductors, ductile, malleable, lustrous, and they form basic components. They tend to be basic. That's why like alkali and alkaline earth metals got their name, is because they form basic solution with water when you put them in water. Nonmetals, of course, we went through these, tend to gain electrons. They dull, poor conductors. This one I think is looking like like breaking up a sulfur chunk here. They tend to form acids in solution, nonmetal oxides, that is. So that's those H pluses. Metalloids, though, have characteristics of both, so you have to kind of like look at the particular ones. Some of them are shiny, some of them are brittle, some of them are semiconductors. They conduct electricity without as much heat, and so definitely different varying characteristics amongst the metalloids. Group trends. Alkali metals are usually soft. They're very reactive. They're the most reactive metal group on the table. Remember, they will oxidize and form a tarnish if you leave them out in air because they're so reactive. So in order to preserve an alkali metal, you have to submerge it in oil. I just like these charts, and you can check them out. They just show the configuration, the melting points decrease, the densities are going to increase as you go down, and then the atomic radius also increases as you go down, and the ionization energy decreases. So you can take a look. It kind of summarizes the group trends. Also gives you density and melting point to refer to and compare these things. They are famously exothermic and react with water very violently. And I know I showed a video of this to my classes last year, but you can easily Google the alkali metals in water video. It's very cool. They can form peroxides. That's not that important. You don't really need to know that. You know, the review of last year, the colors though, lithium was that bright red when we burned it. Sodium's more like a yellow orange, and then the potassium was the lilac or lavender color when you put them in the flame. Alkaline earth metals, same kind of deal. Melting point goes down, density increases, atomic radius increases, and the ionization energy goes down. Same idea here, just comparison. They have higher densities and higher melting points than alkali metals. Their ionization energies are still low, but alkali metals are lower because they're only losing the 1 valence electron. Beryllium doesn't react with water. Magnesium only reacts with steam, but the other ones like calcium, strontium, barium, you put them in water, they start forming hydroxides. And that's a metal, I mean, that's that basic solution that we're talking about. And reactivity, of course, ends up increasing as you go down a group because the ionization energies get lower. So if it's easier to remove the electrons, it's easier to react. Group 6A, so noting this one, this would be the oxygen group. Oxygen's at the top here. And same kind of generalized trend, although this one's a little bit out of normal order. There's always a few exceptions, unfortunately, in chemistry. Density increases, radius increases, ionization energy goes down. But you get variations in what you're having in this group because you have 3 nonmetals. The first top ones are nonmetals. Tellurium's a metalloid, and then you get this radioactive metal. Okay, so you see some variation here within the group due to the fact that you're losing that non-metal characteristic and becoming more metallic as you go down the group. Sulfur is an interesting one, and sulfur and phosphorus and carbon, they have allotropes. Just to want to tell you what this word means. Different forms of the particular element, like there's sulfur, there's sulfur-8, and this one's showing you sulfur-8, where they do have covalent bonds between the molecule, between the atoms in the molecule. And like phosphorus, there's like P4 as well, different versions of phosphorus. And then of course the other allotrope example that's easiest for carbon is the graphite versus the diamond. Both only contain carbon in them, but they are allotropes of carbon, different forms of the elemental carbon. Halogens, most reactive non-metal group on the table, following the similar trends for these guys as the other ones, pointing some of those out to you. And they are these salt formers, of course, because they'll form those anions and be that part of the compound. They have very large electron affinities, negative electron affinities, because they want to gain that extra electron to reach the noble gas configuration. So they give off and release a lot of energy in that process for that stability. They react directly with metals and form metal halides. Some fun tidbits here. Remember, they all start off as diatomics, though. This group's all diatomic. They're all twin molecules in their elemental states. Noble gases, they are the inert group, don't really react. They are monatomic gases. They have very high ionization energies in comparison. Once again, following the same kind of normal trends of the other groups there. And they have positive electron affinities, exceptions to that rule. The idea of gaining electron would, in order to do that, would would put it in a higher energy state, so you would have to give it energy for it to gain an electron. That's why it would be positive here. All right, so final thoughts. Number and type of valence electrons determine the atom's chemistry. Electron configurations are determined. Certain groups have special names. This is besides just the periodic trends. Basic division is between metals and nonmetals on that staircase with the metalloids.